This module is all about alternative methods for path control within the context of routing policies. Let me tell you what this is not. It is not about quality of service, a form of traffic management, and it is not about advanced path control mechanisms like MPLS traffic engineering, necessarily. It is about expanding the knowledge acquired in your CCNP ILT content and demonstrating real-life scenarios based on path control tools. In this first lesson, we will lay out the design considerations and provide a quick peek at other path control mechanisms you may find in your own networks. So, let's put our keyboards and router consoles aside for a few minutes while we lay the foundation for our demonstrations. So, what is path control anyway? Well, let's not do a dictionary definition here, but rather stick to task-oriented and network-relevant topics. If we are talking about controlling paths, then we must assume a certain level of redundancy in our networks at the device and link levels, which results in multiple alternative paths and allows us to think about controlling traffic as related to the path the network chooses for that traffic. Having redundancy does not guarantee resiliency, though. Having a redundant link between two sites, for instance, will not result in effective load sharing if the routers are not configured to redirect traffic if the primary link fails, or if the convergence of the routing function is so slow that applications time out before the backup link is used. So in building up our path control strategy, perhaps the first thing we need to do is think simple routing protocol tuning to accomplish high availability. Your routing protocols may already offer resiliency, but again, it may be a matter of tuning to make recovery fast enough. Along that line of reasoning, why not implement path control with adaptability in mind? In other words, not only when a certain path goes down do I want to quickly choose another path, but also if the main path is extremely congested, I would like to switch paths as well. Performance is also a driver for path control. When we tune our routers to share the load across multiple links, we are aiming at several objectives. One of them is to smartly use all possible paths to increase throughput and bandwidth utilization. Perhaps leaking route advertisements for specific prefixes on one of the links in the figure on top of advertising summaries will tilt the balance of bandwidth use from one link to the other. More advanced path control scenarios involve adjusting network routing in general to specific services that may require specific paths for specific traffic. The question there is, if I want, for instance, to optimize traffic via technologies like Cisco WAS, how do I make traffic flow through the WAS devices? At some point, we need to stop and think about an overall strategy for path control, one that could be called deterministic and provides certain levels of predictability and control. This is not a simple task. When laying out a path control strategy, we should think about the nature of what it is we're trying to control. Traffic is bidirectional by nature. Everything that goes out must come back in. So when adjusting your routing protocol to deploy your path control strategy, think both upstream and downstream. Remember, if you change or tune your upstream routing updates, you are affecting downstream traffic. When you change or tune your downstream advertisements, then it's the upstream traffic that is affected. BGP offers a good set of tools to control both directions of traffic in an internet scenario. But for most routing protocols, it's all about per-hop controls and configuration that combines a series of routing functions that make up your path control toolkit. We'll talk about them in a few minutes. In that sense, and thinking about bidirectional traffic in a resilient network, we find that asymmetric traffic is more common than we think. In this example, traffic is returning via a different local router and a separate path. Now, is this really a problem? Asymmetry, far from being considered a negative, is often desirable. It actually utilizes available bandwidth more effectively, especially in internet scenarios where downstream traffic may have higher volumes than upstream traffic in enterprise networking. Now, if you're inserting state into the network via devices or services, such as stateful firewalls or network address translation, which require symmetrical routing, then sure, you would need to enforce traffic symmetry or tune your services to accommodate asymmetry, but only in that particular area of the topology. Otherwise, it may be generally inefficient and undesirable to try and engineer artificial symmetry, especially in networks which are larger than a handful of devices. Other scenarios where you may need symmetry involve voice networks, where asymmetry introduces jitter and quality of service issues. Routing symmetry per se may not be your ultimate design goal, but optimal routing in terms of network utilization is. Most of the things we do in path control are all about optimal routing based on certain requirements. We should consider those requirements within the context of applications, user experience, and a comprehensive set of performance parameters. In other words, it's not just about delay and bandwidth utilization. It's also about jitter, availability, and overall application performance. The prefixes may be available, but applications may still fail. In terms of specific strategy and tools, ideally there would be a one-button or one-command solution. However, no such thing exists. The scenarios we will demonstrate involve a combination of load sharing, suboptimal routing, routing protocol integration, and other components that eventually require the use of multiple tools, technologies, and configuration commands. We have reviewed these tools in the Route ILT course, and we will put them to good use in this e-learning training. By the way, this is not an exhaustive list. It all starts with good design. Using summarizable address blocks and CIDR, classless interdomain routing, principles are the basis of a stable network, particularly if they are aligned with physical topology considerations. Summarization hides addressing details, but more specifically, isolates routing protocol issues and defines failure domains, creating network stability. Controlling summarization in strategic areas of the network will have an impact in path control. In our example here, we are advertising summaries of the 10.0.0.0/8 network, but also more specific routing information for 10.1.80.0/24 in areas of the network where we need direct access to those destinations. You can see how the resulting traffic flows are more deterministic and also resilient. Other tools here, such as filters, allow more specific control of routing updates and provide security mechanisms to hide certain destinations. Some others, like PBR, can actually bypass the routing function and define a path based on static or dynamic information, forcing traffic into specific destinations like security appliances, NAT devices, and WAN optimization elements. Our demonstrations will show that path control is not an isolated tool or command. It is a combination of several tools, from the basic passive interface command to the more advanced controls based on IP/SLA. It is important, however, to build a strategy around the tools and technologies for path control. By controlling and filtering routing updates in a certain direction, you can affect traffic flowing in the opposite direction and prevent that traffic from reaching those destinations. Through marking or tagging routes, you can define priorities for those destinations along multiple paths, giving you the option to use those paths in a deterministic order. A common example is internet routing, when multiple exit points exist out of a certain network. You can use route maps to tag and define priorities for this particular scenario. Remember, each routing protocol has specific capabilities that will help you implement the strategy more effectively. Tangible things like automatic summarization in the case of EIGRP, area summarization in the case of OSPF, or changing metrics and tagging prefixes of external routes in OSPF during redistribution. Be sure to understand those specific capabilities of the routing protocols in use. The examples listed here are related to OSPF and EIGRP. In this lesson, we will demonstrate some of these scenarios to illustrate specific configuration examples of path control. Some of them are common situations of path control being implemented to fix suboptimal routing, perhaps caused by scenarios of redistribution with multiple edge routers. Some others aim at simple configurations where administrative distance is used to inject floating static routes that serve as deterministic backups for branch office connectivity. Notice the variety of objectives that result in some sort of path control mechanism. We will see strategies in action during our directed demonstrations coming up in our next lesson. So, we are now ready to demonstrate some of the concepts we have discussed. But first, let's take a quick look at additional path control mechanisms that you may encounter in your enterprise networks, at some point now or in the future. These advanced topics are becoming more commonplace as technologies mature and find their way into corporate networks. Some of them are actually built around network design issues using technologies such as virtualization. Some others point to targeted mechanisms that are built around the path itself, along multiple hops, and not around hop-by-hop configurations. Such an example is MPLS traffic engineering, or MPLS-TE. Let's take a quick look at some of the benefits of these methods. Optimized Edge Routing, or OER, is one of them. Intended for sites using multiple Internet or WAN service providers, OER uses tools like IPSLA to automatically detect network service degradation and make dynamic routing decisions and adjustments based on criteria such as response time, packet loss, jitter, path availability, traffic load distribution, and others. This is unlike normal routing, which is focused on detecting a routing path, rather than the condition of the service over that path. Normal routing mechanisms like routing protocols use static routing metrics to do path selection. So, these edge routers, called border routers, monitor information about route prefixes through traditional routing protocols and gather performance statistics over each external interface, in this example using IPSLA. This information is periodically reported to another router called the master controller. If the prefixes and exit links comply with a configured policy based on performance and service metrics, routing is left as is. If not, a policy-based decision is made by the controller and notification is sent to the border routers, which could add static routes or change routing protocol parameters to change the path. Virtualization is another advanced method you see more and more in enterprise networks. One of its benefits is traffic segregation across a common physical and network infrastructure. For instance, virtual routing and forwarding tables, or VRFs, are nothing more than virtual routing tables, which you can have separate per department or group of networks, while still talking about the same physical router. The employees' routes would be separate from the guests' routes by belonging to two different VRFs. VRFs can then be associated with several virtualization and traffic segregation elements on the network, like VLANs or VPNs, to provide an end-to-end segregated path across the network for those departments, using separate links. So here, path control is based on a design decision to engineer different paths and do path control with network virtualization technologies. WAN optimization using Cisco technologies such as Wide Area Application Services, also known as WAS, is a good example of the use of policy-based routing to adjust the path of traffic based on advanced services for that traffic. You will also see technologies such as WCCP, the Web Cache Communications Protocol, performing a similar function, which is to have routers redirect normal traffic flows into the WAS devices, allowing them to implement a series of data reduction, flow optimization, and application acceleration services, and then have them route the flows back into their normal path across the WAN. With data center consolidation trends on the rise, this type of path control requirement is becoming common in branch office scenarios. Hopefully, we have laid out the reasoning behind path control mechanisms in terms of design objectives, including resiliency, adaptability, and predictability. Key to deploying an effective path control strategy is understanding the nature and characteristics of the routing protocols and traffic flows you're trying to control, as well as the available tools to implement that strategy.